Hi everybody, and welcome to Friday's virtual class. So a reminder that Monday you will have an exam, and you will need something to write with and a calculator. Other than that, I will give you any reference materials you need. Posted on Blackboard is a sample of the data sheet that you will be given, as well as an outline that lists all of the things that we've covered that you should be comfortable with and study for the exam. So what we're going to do right now is we are going to go over the solutions to the practice problems that I gave you that covered the final bit of ligand binding material. So here we go. All right, so question number 1 is bisphosphoglycerate is an allosteric modifier that binds to the central cavity of hemoglobin. BPG affects hemoglobin affinity for oxygen by binding at a site different than the oxygen binding site and promoting a shape change in the molecule. The result of BPG binding is that oxygen binding curves shift to the right. When the small molecule is the same as the normal ligand for the protein, this interaction is called homotropic, as it is for oxygen and hemoglobin. The interaction of BPG with hemoglobin is heterotropic, since BPG and oxygen are not the same and do not bind to the same site. This is what we covered in the very end of my previous video. The molecule BPG binds to the deoxy form of hemoglobin in the central cavity. Explain why that makes sense for oxygen delivery and why BPG is said to stabilize the deoxy or T state. So, that's the question. And so here are the things that you should consider. First of all, when you see the central cavity, it should ring a bell in your mind or signal to you, hey, that's one of the structural differences that we talked about between the T, the low affinity, and the R, the high affinity states. So, the size of the central cavity is a distinct difference between our two structural states. The cavity is wider in the T state. That's point number 1. And so, we're told that BPG binds to the deoxy form. So, it's binding to the form where it's wider, and it's binding in that cavity. So how can it stabilize that state? Well, BPG binding in the central cavity is kind of like putting a wedge in the door, like we do in the lab, so that the door stays open and we get some air circulation when it's really hot. So the BPG is going to stick in the middle of that cavity, okay, and it's going to prevent that shift to the R state by just sort of physically blocking things. So you may get that, if oxygen tries to bind, you may get that helix like trying to move and trying to shift, but it really can't because it's bumping into other atoms. Okay, so it's our big steric wedge that's going to hold that molecule in the T state, where it can bind oxygen, but it binds it with a much lower affinity. Okay, so the T state has a lower affinity for oxygen, and so any molecule that kind of shifts it into this state is going to aid in oxygen delivery. So when hemoglobin arrives at a tissue with a lower oxygen pressure, equilibrium is going to cause more O2 to fall off of the lower affinity, okay, because differences in affinity reflect differences in association and dissociation constants, and remember that those are connected to our equilibrium sweet spots. So the T and the R state are going to have different equilibrium ratios that rule oxygen binding behavior. All right, so the second question was, how do the levels of oxygen in the atmosphere compare at sea level versus high altitude? And then you were given a diagram and you were asked to shade it to show the oxygen in the lungs at high altitude. And then the second question was to draw an extra curve on the graph to represent the hemoglobin binding of oxygen in people adapted to high altitudes. Okay, so these questions were the first parts of those questions excuse me. You get to hear me sneeze on video. Lucky you. All right, so the first parts of these questions were things that you should have or could have looked up. So, excuse me, there I go again. All right, so the figure on the right represents what you should have found, at least for partial pressure of oxygen at high altitudes. So we started with our hemoglobin and myoglobin curves that were shaded just like when we were first looking at those binding curves. Okay, so here's the pressure in the lungs, here's the pressure in the tissues. Now, oxygen levels, we know, are lower at high altitudes. So it turns out that, instead of about 100 torr, the pressure of oxygen at 50 torr is at 18,000 feet is about 50 torr. Okay, so we've got much lower levels of oxygen. And so that brings us to, this sort of midpoint on our hemoglobin binding curve. Okay. Now, individuals adapted to high altitude, their curve is shifted to the right. Okay, so again, it looks as if they have a lower affinity for hemoglobin because they have a higher P50 value. Okay, now, does it make sense to you that if you're living at high altitude where oxygen is less prevalent, you would want a hemoglobin with lower affinity? I mean, to me, at first glance, that wouldn't make sense. I would think, no, I want much higher affinity hemoglobin so I can pick up more oxygen. But the key point is not how much oxygen are you going to pick up, it's how much oxygen are you going to deliver. Okay, because the whole point of hemoglobin is not simply to pick up oxygen and hold on to it for all it's worth. It only is useful if it can pick up some oxygen and then hand it off in the tissues. Okay? So what happens is individuals with that are adapted to high altitudes. So sports teams will, when they're playing in Denver, Colorado, will go out there, a week or two early or however early they can get out there so that their players' systems can adapt. And what that adaptation involves is producing more bisphosphoglycerate, okay, BPG. And that BPG, we know, assists in oxygen unloading because it stabilizes the T state. So if we look, a person unadapted to high altitudes may pick up a little more oxygen in the lungs. Okay, so they have 75% or 70% of their oxygen or of their hemoglobin is loaded with oxygen versus 60%. So there's a small difference there. Okay, but what happens is that people, when you get into the tissues, people who are adapted to high altitudes are delivering a greater percentage of that. So, let's look at just the midpoint 30. They have delivered, if they're starting at 60%, and they deliver, about 40% of what they've picked up. Whereas if we're looking at people without adaptation, they go from 75 to about 60%. So they're only delivering, 15 to 20% of what they picked up. Whereas once you're adapted to high altitude, you're delivering a lot more of that oxygen to the tissues. And that's how BPG can help us at high altitudes. So during that 2 weeks that you're adapting to the altitude in Denver, what happens is your body upregulates the amount of BPG that it makes, among other physiological changes. But you make more, that and that is going to be found particularly in the tissues. Okay, and what's going to happen is that even though you pick up a little less oxygen in the lungs, you deliver a much greater percentage of it because you've got this molecule that stabilizes the low affinity state, and it's going to bind to that state. And again, equilibrium is going to cause you to deliver or unload more oxygen. All right, question number 2. We're talking mutants. All right, so in the mutant hemoglobin, known as HB providence, an asparagine residue in the beta chain replaces lysine 82. In normal hemoglobin, lysine 82 projects into the central cavity of the hemoglobin molecule. Predict the effect of the lyse to asparagine mutation on the affinity of allosteric modifiers relative to normal hemoglobin, and describe the effect the mutation would have on the function of HB providence. Okay, what do we think of anytime you hear something about the central cavity? What binds there? Our old friend, the only allosteric modifier we've talked about so far, BPG. Okay, so if you went and looked at the BPG molecule, you would see that it is negatively charged. Okay, and again, the way it binds to hemoglobin is through an electrostatic attraction to positively charged lysine residues in the central cavity. Okay, so so what should you know about hemoglobin? It has two structural states. The size of the central cavity is different in the two states, and now we know that the central cavity contains positively charged lysine residues, and they attract negatively charged BPG, and that's its main mechanism of binding. That is the intermolecular force, okay, that drives BPG to bind to hemoglobin. All right. So let's think of what happens when you mutate lysine to asparagine. Lysine is positively charged. Asparagine is polar, but it's uncharged. So asparagine can hydrogen bond, but it can't be involved in a strong electrostatic interaction between a positively charged thing and a negatively charged thing, right? So the affinity of the mutant hemoglobin for BPG is going to be lower because you're getting rid of those positive charges that are attracting your negatively charged BPG. So because BPG helps with oxygen unloading, okay, this mutant hemoglobin, which has a lower affinity for BPG, is going to be less effective at unloading oxygen in a real biological system that's going to have BPG present because it's not going to respond to BPG. Okay, so HB providence, individuals that have that mutation cannot unload oxygen as well as the rest of us who are capable of binding to BPG. Okay, question number 3. Protein A has a binding site for ligand X with a dissociation constant of 10 to the minus 6 molar. Protein B has a binding site for ligand X with a dissociation constant of 10 to the minus 9th molar. Which protein has a higher affinity for ligand X? Explain your reasoning and convert Kd to Ka for both proteins. Okay, so because the Kd and the Ka are reciprocals of one another, it's easy to relate them in terms of affinity. So remember, dissociation constant is referring to the process of the ligand X falling off of the protein. Okay, so it's this reverse process is the Kd. So, do we want a Kd to be big or small for high affinity? Well, Kd, remember, if it means we're falling off of the protein, we want that to be low. Okay, so let's actually do, so the protein with the lower Kd is going to have the higher affinity because less of our ligand is going to come off. So which of these is lower? We've got 10 to the minus 6, which is a small number, and 10 to the minus 9, which is a much smaller number. Right? So protein B is going to have a higher affinity. So, and if we look, and we can turn that into an association constant by just taking the reciprocal of that number. So are association constants, because sometimes it's easier for people to think of affinity in terms of the thing going on instead of the thing not falling off. All right, so if we look, protein A has an association constant of 1 times 10 to the 6th per mole, and protein B has 1 times 10 to the 9th per mole. Okay, so association constants bigger, higher affinity. Dissociation constants smaller, higher affinity. So in this case, protein B is our molecule that has the higher affinity. Question number 4. Under appropriate conditions, hemoglobin dissociates into its 4 subunits. Isolated, that should be an alpha subunit. Isolated alpha subunits bind oxygen, but the oxygen saturation curve is hyperbolic instead of sigmoidal. In addition, the saturation curve is not affected by the presence of protons, carbon dioxide, or bisphosphoglycerate. What do these observations indicate about the cooperativity and allosterism observed in intact hemoglobin? All right. Well, we haven't talked about these 2 allosteric modifiers, but we do know about BPG. So we'll frame this answer in terms of BPG. So what are the points that we should consider? First of all, the first thing it tells us is the saturation curve changes when you take an isolated hemoglobin subunit, okay? And it changes shape, hyperbolic instead of sigmoidal. Okay, so sigmoidal curves represent cooperative systems, and hyperbolic curves are indicative of non-cooperative systems. So cooperativity is distinguished by a sigmoidal binding curve. So if our curve changes to be hyperbolic, the oxygen saturation curve for hemoglobin is hyperbolic when you have an isolated subunit, and therefore no cooperativity and binding is observed. Okay? So, and because it's not affected by allosteric modifiers either, what we can consider is that when you have an isolated subunit, you lose your cooperativity. So you can infer that the root cause of cooperative binding behavior is due to interactions between the subunits. Because when the other subunits are not attached, then you don't see any cooperative behavior. And the same thing about allosteric effectors. Okay, if you isolate the subunit, you do not see any influence of these allosteric effectors, and so that allosteric behavior must also be related to the protein having quaternary structure, because when there's no quaternary structure there, you don't get allosteric effects. Question number 5. All right, with the use of site-directed mutagenesis, which just means that we can take a single position in our protein and we can change the amino acid that's at that particular site and see what its impact is on the function of the protein. So, we've made a hemoglobin in which the proximal histidine residues in both the alpha and beta subunits have been replaced by glycine, which just essentially means that, all right, we've gotten rid of the histidine side chain, we've replaced it with something very small. All right, the imidazole ring from the histidine residue can be replaced by adding free imidazole in the solution. So here's what imidazole looks like. Okay, just imagine it would connect to an amino acid if it were the side chain of a histidine, but here it's just free imidazole. So it's the same functional group, but it's not attached to anything. It's just freely floating in solution. Okay, so would you expect the modified hemoglobin to show cooperativity and oxygen binding, and consider it with and without added imidazole? Why or why not? All right, so first let's consider this modified hemoglobin without imidazole. Okay, so we don't have anything that can bind to the heme iron without the added imidazole. So oxygen will bind to, the heme iron, but that oxygen binding will have nothing that can transmit information to the rest of the heme molecule. Okay. So now let's consider when we add imidazole. So now there's an imidazole ring there, right? And that imidazole ring could bind to the heme iron, much like the proximal histidine side chain could in the non-mutant. However, there is no connection between this free imidazole that you're adding and the protein. Okay, this isn't like the histidine side chain that's linked to the F helix. It has the same functional group as that histidine side chain. It can coordinate to the heme iron, but it's not attached to anything. So, although there would be a change in the heme, the porphyrin ring when the oxygen binds, and it would change the position of the imidazole without any connection between the imidazole and the protein. No conformational change would be communicated to the protein. So no cooperativity would be seen. Okay, so what it means is that each individual heme group in your hemoglobin tetramer would behave as if it were just an isolated subunit. It would have a lower affinity for oxygen, and binding at one site is not going to affect the ability to bind at the other sites. Okay, and I believe that was our final question. So I'm going to stop there, and if you have any questions, I will have an office hour on Sunday, but I will also be available by email and between 9 and 10 in my office before the exam. Actually, between 9 and 9:45 in my office before the exam. All right, have a good weekend. Bye.